squared operations. Okay? Because you have to modify every row of the matrix. One way of interpreting, you take the first row and subtract it from all the other rows, but you can also think in terms of elimination of variables. So it's n squared because you modify, you basically add the scalar multiple of one row to each of the rows. This is n squared, and you take n steps. This is n cubed. So the question we talked last on Tuesday, we talked about Strassen. So can we use Strassen here? Algorithm for solving linear systems, or okay, for Gaussian elimination? What do you think? Okay, you think no. Anyone has another opinion? Okay, yes you can. Maybe not very practical, but at least the complexity, actually the asymptotic complexity of solving linear systems for dense matrices is the same as the complexity of multiplying matrices. So in order to show that, we again go to the block dividing block correction. So we have a block matrix with blocks, and that's what we want to do. We want to compute the block LU factorization. So here, this is not lower triangular matrix because this matrix is not required to be triangular, right? Here, but it's block triangular. And if we have computed this factorization, we can further factorize these blocks to get the LU factorization. So if you know how to compute, so we assume like usual in the recursion, we can compute LU factorization of a small matrix, and then we want to, using this knowledge, compute LU factorization of twice larger matrices. And we use this block representation. So what we basically have to do, we basically have to write down equations for these blocks. I don't know if I have, yeah, I don't have the formulas here. I want to spend some time on it. Probably I can spend a little bit time on that. It's not so convenient to do this. Okay. Probably have to switch on the internet for this, otherwise we'll get messages. How to do that? Sorry. Okay, not that much. Let's hope no one writes to me doing this. So, what do we have? We have a block matrix. And we have L11, L12, L22, 0 times the upper triangle U11, 0, U12, U22. So, we basically have to multiply this, right? So we have the product L11 times U, so it's like this. Also easy to multiply 2 by 2 matrices. Here times here, what would be here and here, so it will be L11, U12. Here you will have this one times this one, so it will be L12, U11. And here you will have, L12, U12 plus what? L22, let's check, I think I'm correct, right? So what we have? We basically have here this block, And we can compute the factorization of A11 block, right? So we need to make one elimination of order n over 2, right? So if we know L11, we can use it, and we can make it up a triangular by default. We can take the equation with A21 and this guy. A12 equals L11 U12. So we know L11, and it's lower triangular. So then we can basically compute U12 equals L11 inverse, and computing the inverse of lower triangular matrix is n squared. That's what you can show. This lower triangular matrix, the inverse of lower triangular matrix is still a lower triangular matrix, can be done as n squared. And then you multiply it by U12, and this is matrix multiplication, right? Matrix multiplication causes n to the power omega. Here we can use fast algorithm. The same for here, and if you know, we know from this equation, we know U12, from this equation we know L12. If we know this term, and then we only need to factorize the difference between A22 minus L12 U12. So basically we have several matrix multiplication of smaller sizes and two factorizations. And this is sort of informal, well, more or less formal proof. It can be put into a formal proof that solving a linear system, computing Gaussian elimination, can be written in terms of matrix multiplication of smaller blocks. Okay. So, and the question that we need to discuss further is the stability and maybe even existence, right? So so this decomposition is nice. If we are able to compute it, we can factorize and solve linear system. So the main assumption that this decomposition doesn't fail is that we do not get an equation where the coefficient with respect to the variables that we are eliminating is equal to 0. So a LU decomposition corresponds to the diagonal pivot. So you take you eliminate the first equation from first unknown from the first equation, second unknown from the second equation, and so on. So if you do not divide by 0, you are guaranteed to converge. And the question is, what is the class of matrices for which there is a guarantee which can be checked that you will not be able to divide, you are not dividing by 0. So this class is important. It's called so-called strictly regular matrices. So informally, it means that you have to have large elements on the diagonal of the matrix, right? Then you will be dividing by something not very small, but you have to have more. You have to formally define what does it mean to have diagonally dominant. But the strict definition, the strict characterization still comes in terms of determinism. So the question that we are answering, when the eluding, you are given a matrix, when the eluding composition does exist. So it exists when the matrix is strictly regular if all of its principal minors, so the principal minors, I call it pivots, but minors, I don't know. Minors. No, I think it should be minor. So we have the matrix, and the minor is a submatrix. Sometimes you call it determinant of it, but what you have to have is that you have the first one is 1 by 1. That is okay. You have squares here, but I've written not very aligned to it, but it doesn't matter much. So you have 1 by 1, 2 by 2, 3 times 3, 4 times 4. You have A1, A2, and so on. So like a Python notation would be something like that. And all of these matrices, all AKs should be non-singular. So they have to have non-zero determinant in the exact arithmetic, or they have to have full covariance. In this case, a Lydic composition exists. If and only if. Exists. The reverse is also true. Right? The reverse is very easy to check because the principal minor of a matrix represented as a product of a lower triangular matrix times an upper triangular matrix is the principal minor of A, which is again lower triangular, times the principal minor of U, which is upper triangular, and the lower triangular matrix is non-singular if the elements of the diagonal are non-zero. The same holds for the upper triangular matrix. Okay. So, yeah, so that's. But the other way is more complicated. So the other way is more complicated. So you basically have to show what means another way. So if you have a strictly, you have to show that if your matrix is strictly regular, then it has a Lydic composition. So basically you do it by induction. So suppose you know that for all matrices of side, for one by one case it's obvious. So suppose you know that for all n minus 1 times n minus 1 matrices with non-singular minus, a Lydic composition exists. And then what we do, sorry for this thing. So we can write down again as a block. So you might have noticed that block notation can be very useful, but here the block sizes are not equal. But this is an n times n minus 1 matrix, and these are like bordering of this matrix. So this is a column vector, and this is, by the way we write row vectors. So row vectors we write as a transpose of a column vector. So row vector is 1 times n matrix as a transpose of a column vector. This is just a number, and we need to show that this has. We need to show that this has the Lydic composition. What we do again, we do block elimination. So we multiply this matrix from the left by this matrix. And that's what we get. We get upper triangle matrix. But what we need to show, that this guy is still strictly regular. And yeah, so the main question is to show that this guy is strictly regular. I forgot. I think I do not have this proof. So let's get back to it after the 5 minutes break.